Okay, so this is the follow-up reflection review for the homework questions and the quiz that I gave you. Those are found on Schoology in the quiz. These are the equilibrium questions. So these are the assignments. If you're wondering where these questions came from, these came from the UPCO, the New Hotness Review Book, on pages 97 through 99. Before I go over those, I want to do a quick review of some of the material in here, and then we'll jump right into this. So let's get ready. For equilibrium reactions are reactions that can be reversed. So not all reactions can do this, just some of them. Remember, here's the Haber process. The important part to remember about equilibrium reactions is that the forward reaction and the reverse reaction, they have the same rate. Has nothing to do with the concentrations being the same, the amount on each side being the same, any of that. The only part is the rate of the forward reaction, the amount of this stuff changing, reactants changing into product, is the same as the rate of the products changing back into reactants. That's what the equilibrium is all about. We talked about the square brackets. Square brackets, those mean things that are in equilibrium. Anytime you see the square brackets, that says the concentration of NH3 or ammonia. Okay, the only substances whose concentration can be measured are liquids, gases, and aqueous substances. And the only one for which pressure affects are gases. So all of that needs to be remembered. So Le Chatelier's principle has to do with stresses applied to a system. And stresses are things that force reaction in one direction or the other. So again, we'll take our famous equation here, the Haber process. If we want to make more NH3, if we want to favor the reaction to go in the forward direction, if we want our reaction to go this direction, okay, what we need to do is either add reactant, add stuff to this side, or we need to take away stuff from this side. Those are the two options. With this one, also what we can do is pressure, because all three of these substances are gases, all right? The side with fewer moles of gas is going to be favored under high pressure. Here we see on this side, on the reactant side of the equation, we have 1 mole of nitrogen, 3 moles of hydrogen, for a total of 4 moles of gas on the reactant side. On the product side, we have 2 moles of ammonia, so we have 2 moles of gas on this side. So if we increase the pressure, increasing the pressure is going to favor the forward reaction. It's going to go forward because we have fewer moles of gas on the product side. So that's what we're talking about, a stress. Le Chatelier talked about adding and removing temperature, adding and removing heat, adding and removing pressure, adding and removing concentrations. All of those are different kinds of stresses. Visualization of stresses. So imagine we have a balloon. This is one continuous balloon inside a toilet paper roll. If I squeeze on the left side, what's going to happen to the right side? Well, it's going to get bigger. And so we think of the reaction as moving in the forward direction. So if I squeeze over here, if I squeeze on this side, all right, squeeze there on this side will get bigger. Okay. Another analogy is the buckets. These are 2 buckets that are connected by a pipe in between them, and they're at the same level. They are at equilibrium. That just means the rate of water going from this bucket into this one is the same as this one into this one. Notice these are 2 different size buckets. So therefore, this bucket here on the right will have more in it than the one on the left. Furthermore, all we're concerned about is the level. They are at equilibrium. Okay, doesn't mean they have the same amount on the other side. It just means the rate of this, the left side going to the right side, is the same as the right side going to the left side. However, a stress could be applied is if we were to add stuff into this side. We add stuff into that side, add more water. What's going to happen? Well, as you add more of water into here, all right, the water is going to flow from this side, the left side, over through the pipe to the right side. So it favors the forward reaction. Similarly, if we were to take water out of the right side, again, water would flow from the left into the right to make up that difference, the equilibrium, the stress applied to the equilibrium, and it would favor the forward direction. And the same happens in the opposite direction as well. Let's get back to these questions. All right. First question, let's look at it. First question says a solution in which an equilibrium exists between undissolved and dissolved solute is always, well, that's what a saturated solution is. A saturated solution is a solution that is equilibrium. The stuff on the bottom is dissolving as stuff in the solution is undissolving. That's a saturated solution by definition. So here we have it says a flask is partially filled with water and stoppered after a period of time. The water level remains constant, just like this water bottle. See if you look, it's got the cap on it tight, and you can see the condensation on the inside here. What's happening is water from the down below here is evaporating, but at the same time, water vapor in the air is condensing, and so it's maintaining this same level here. So the rate of the condensation equals the rate of the evaporation. Doesn't mean the vapor is equal to the water. It just means the rate of the both are the same. So the rates of condensation and evaporation are equal. The rate of evaporation equals the rate of condensation. So number 4. So this is an equation here that shows you hydrogen, iodine, and hydrogen iodide. All three are gases. And this says which statement is always true when it reaches equilibrium. Here we're using those square brackets. So the way this reads is the concentration of hydrogen times the concentration of iodine is greater than the concentration of hydrogen iodide. That is not something you need to know. But what you do need to know is the concentration of hydrogen, iodine, and hydrogen iodide, they remain constant. Number 4, that is what's happening at an equilibrium. Don't worry about how much of each one, just know that the concentrations remain constant. They're not equal, they are constant, meaning unchanging. As the reactants change in the product changes into reactant. Number 4, when this reaction reaches a state of equilibrium, the concentration of the reactants, again, the concentration remains constant. It becomes constant once it's at equilibrium. It's not getting any bigger. It's not getting any smaller. That's not to say that it's not changing from reactant into product. It still is. It's just that the product is changing back into the reactant at the same rate. That's equilibrium. Again, this question here, talking about an equilibrium expression. This says which statement's always true? Do you need to know that the rate of the forward reaction is equal to the rate of the reverse reaction? That is what's always at equilibrium. All right? Kind of beating this dead horse, but I want you to make sure you understand what this is. Here's another equilibrium. This is a phase equilibrium. The solid carbon dioxide is in an equilibrium with gaseous carbon dioxide. And it says as the pressures increase, it's going to favor what? Well, as you pressure increases, pressure only affects gases. So this gaseous carbon dioxide is going to change it back into the solid carbon dioxide because it favors the side that has fewer moles of gas. So it's going to go in the reversed reaction. So as the pressure increases at a constant temperature, the amount of CO2 gas will decrease. 7 saying, which system at equilibrium will shift to the right, so in the forward direction, when the pressure is increased? Well, that's going to favor the side with the fewer moles of gas. While this side, we have solid. Over here, we have aqueous, no gases. Pressure is not going to have any effect on number 1. Here we have liquid and aqueous again. No gases. Pressure is not going to have any effect. Here we have a gas. We have an aqueous. Pressure will affect the gas, but it will not affect the aqueous. So what's going to happen is you increase the pressure. It's going to go from gaseous into the aqueous, and more ammonia will be dissolved. So that's your answer number 3. And again, here you have no gases, so it's only the one with the gases. Number 8. Okay, now what we're showing here is we have this reaction here, and it says the rate of the forward reaction can be increased by adding more SO2 because, well, SO2 is on the reactant side. As you increase the concentration on the reactant side, it's going to force the reaction to go, that's a stress applied to the system, to go forward. So this is the rate of the forward reaction can be increased by adding SO2 because the number of molecular collisions between the reactants is going to increase. You're just going to have more SO2s running to O2s, and it's going to make SO3s. So that's just why. Has nothing to do with endothermic. The reaction is not endothermic, it's exothermic. All of that is true. So number 2 is the only answer. Number 9, this is as the temperature increases the rate of the forward reaction. Well, temperature is heat, and over here we have energy on the product side. So if we add something to this side, as the temperature increases to the whole system, this is going to force it back in the reverse direction. So as the temperature increases, the rate of the forward reaction will decrease. It's going to go in the reverse direction. Here's a bottle that's open, all right, and the ammonia that's in the solution and the ammonia that's above the solution, they are not at equilibrium. How do you make it at equilibrium? You need to cap it off. You would stopper the bottle. Otherwise, what's going to happen is all the ammonia is just going to eventually evaporate out, and it's just going to keep coming out until it's all gone. So the next term they're going to talk about is entropy. And entropy is the measure of disorder in a system. Greater entropy means greater disorder or less order. So here's an example of a visualization. So over here we have a pile of Legos, and over here we have Legos all made into a nice house. This has high entropy. This side is low entropy. High entropy is great disorder. Low entropy is less disorder. Another example, the solid, liquid versus gaseous phases of a matter. Here a solid is all nice and orderly, low entropy. Liquids a little bit more entropy, more disorder than the solids, and then gases are even more disorder than the liquids or the solids. So high entropy for gases, low entropy for solids. Here's another example. Here we have a ice crystal. Ice crystals are very organized patterns of water molecules. That's high order, low entropy. Over here we have water molecules running everywhere. That's high disorder. All right, so that's high entropy. High entropy, low entropy. All right, so let's get to these questions. Sample of water at 20 degrees Celsius in equilibrium with its vapor in a sealed container. When the temperature increases, the entropy is going to be, well, it's going to increase because more waters could change into water vapor. So the entropy of the system will increase. Ice, change from ice into liquid. The change of water solid, the changes in H2O involve, well, you're adding energy, so it's going to be an absorption of energy, and as it goes from a solid to a liquid, it's going to be more entropy. So an absorption of heat and an increase in entropy. So number 3. 13, a gram of water vapor changes to water liquid. Well, gases have higher entropy than liquids, so the entropy is going to decrease. Which one results in an increase in entropy? Liquid to gas. There's an increase in entropy. Gases to gas, 4 moles of gas to 2 moles of gas, that's a decrease in entropy. We have 3 moles of gas to liquid, that's a decrease in entropy. We have here 3 moles of gas to 2 moles of gas, that's a decrease in entropy. Number 1 is your only answer. 15, it says a gram sample has the greatest entropy when it's in the gaseous state. Gases have more entropy than solids, liquids, and crystallines. And this last question here. Right now at the beginning, there's argon on this side, neon on this side. You open the valve. They're all going to be mixed up. Mixed up means more entropy. Hope this helped. If you have any questions, feel free to contact me through Remind.